Okay, great. All right, so good afternoon. My name is Justin, and I'll talk about some, how shall I say, the kind of the benefits that we got from implementing a distributed learning framework on top of the RAD lab stack. So with this talk, I'll just give a brief overview of Spark, as well as the, oh, is there something? Okay. Did not realize that, okay. Should I try that?
Yeah, okay. I would just pull it over to the other window.
Oh, really? Okay.
I think that's the problem.
Sorry.
That's okay.
Mac noob over here,
way.
so.
There we go.
Okay, cool. Well, let's,
Maximize it.
yeah, let's see. And then I'll have to go back to full screen, right? Sweet.
Yeah, it's not going to work.
It's not going to work, huh? All right. Let's see. See that? Yeah, sure.
Yeah,
All right.
just do it.
Okay. Well, a few technical difficulties. We'll have to live with that. All right. So yeah, I'll talk about some experiences that we had writing a distributed learning framework on top of the RAD lab stack. And I'll just kind of give an overview of Spark, as well as the application that we wrote on top of Spark. So the context in which Spark emerged was that there are a lot of new specialized frameworks being written for distributed computation, MapReduce, Dryad, Pregel, among others. And their job is to provide high-level program extractions to kind of hide the scale and the fault issues away from the programmer. And as I mentioned, they're specialized. They might have acyclic data flows. They might have graph-type data flows. And a question that we wanted to ask is, well, is there a unified abstraction that we can adopt to express a broad range of these kinds of distributed applications? And to that end, we decided, well, let's write a new framework. So Spark was a framework that emerged as a special case of the Mesos project. But now we're pushing it in a different direction, which is to make it a little more general purpose. So we write it to run on Mesos. And this actually dramatically simplified the code base for writing this, because Mesos decouples resource allocation from the framework, the Spark code base ended up being about 4,000 lines. At least for Hadoop, a code base of about 30K lines, a lot of that's dedicated to resource allocation, fault tolerance. Because of this decoupling, things were much simplified for writing Spark. So Spark itself is a new distributed computation framework. It's not a derivative of Hadoop. It's actually a new code base written from scratch, based in Scala. The key concept behind them is that of a resilient distributed data set. So you can think of them as parallel arrays. And with these parallel arrays, you can work with them in memory for caching them if you need to work with iterative and interactive style jobs. You transform these RDDs, these are using maps, filters, and so on. And there's a limited form of shared memory at the moment in the form of broadcast variables, that is the one-to-many type of data sharing, as well as accumulators, which is a many-to-one style. So to give you an idea of what a Spark application looks like, I'll kind of talk briefly about a distributed logistic regression example. So in this, what we're trying to do is we're trying to learn a classifier that computes partial gradients based on data points that are sitting in a high-dimensional space, and then taking those gradients, sums them up, reduces them, and comes up with a new version of a decision boundary to separate good examples from bad examples. So what's happening here is that the base data starts off in the SCAD store. And we do some initial parsing in the form of a map. And then we cache the data set in memory. From there, we do this iterative procedure where we can compute the partial gradient. This is, again, a map procedure. And then sum the gradients using a reduce. And the way that the RDDs work is that the first time around, the access will go all the way to the persistent store where SCADs is. But on subsequent iterations, it's possible to hit the cache and thereby speed up the iteration time in subsequent loops. So I'll mention that programming in Spark was convenient. You could concisely express operations. Components of Spark were modular, so if we wanted to swap in a different broadcast algorithm or a different shuffling algorithm, that was possible. When combined with SCADs and Mesos, it offered a lot of flexibility in terms of being able to write the code once and to deploy it, say, on the local machine or on a distributed cluster. And I'll talk a little bit about experiences implementing our distributed learning algorithm for Twitter spam classification, the work which has been recently accepted to the Oakland Security Conference this year. And that work will be presented this May. So I'll just, since the animations don't work, I'm just going to kind of skip over this. So, imagine you've got a tweet or a SCADr message, and it's got a link in it. How do you make the determination whether to visit it or not? Now, when you visit a site like this, you'll be taken through redirects, which, one or many, which finally gets you to the end page. And there's a lot of information that you can utilize to come to a decision on whether to visit a page or not, right? You might look at the HTTP headers. You might look at, this server is hosted in this particular autonomous system or in this particular city. It may contain Flash objects, JavaScript, funny JavaScript objects, or have objects included from suspicious domains. But what we do with all that data is that we canonicalize it, we turn it into a mathematical vector, which we use for classification. So those were those little pluses and minuses that you saw earlier in the example. So the data we're dealing with are labeled feature vectors. To have a data set where we know some of the data is good, some of the data is bad, we actually had to do some retroactive labeling, looking at blacklists and taking a look at historical data to label the examples as good and bad. And the reason we wanted to use Spark is because we wanted to do training relatively quickly. When you're approaching a deadline, you kind of have to run 150 different experiments. You want to be able to get those done quickly. And so in-memory computation was pretty key. So the straightforward approach, which I explained earlier for distributed logistic regression, was insufficient because we ran into a few problems with that. And I'll explain how we used elements of the RAD lab stack to address these problems. The first was unoptimized data storage and transfer mechanisms. The second was memory exhaustion on the master and the slave. And finally, the third was kind of more algorithmic. It was slow per iteration convergence of the decision boundary. Now, to address the first point, we had to kind of take a look at some of the basics of our implementation. Because if you have an unoptimized data storage implementation, inefficiencies get magnified at scale. And so we had to look at several things: custom serialization, truncating feature names, short-circuiting various vector operations to get things up to speed. And something that's ongoing, not something we did for our initial submission, but something that we're looking at right now, is integrating to bring SCADs into the picture instead of the Hadoop file system. Right? And this is really convenient, right? Because if you've got interactive apps such as SCADr, Gradit running, storing their data in SCADs, then you can reference that same data for batch analytics. And the RDD abstraction actually provided enough of a narrow waist kind of interface that we could implement in Spark. We could implement a 60-line new kind of RDD to be able to read from SCADs. So I mean, the way that SCADs was structured, the way that Spark was structured, made this pretty convenient. So in terms of where this brought us in terms of implementations, we were able to reduce some of the communication overheads between the different stages. But we still ran into memory exhaustion issues on the master and the slave. And we addressed these two ways. There's a systems remedy, and there was an algorithmic remedy for this. So as far as the system side remedy, before we were aggregating a lot of data in one master in one step. Instead, it would behoove us to actually parallelize the summation of different parts of the feature space among the slaves. So the shuffling was pretty critical for this. Algorithmically, we applied regularization. That is, we want to reduce the number of non-zero entries in our classification weight vector. And so for that, we used L1 regularization using the Phobos algorithm. Now, implementation-wise, I mean, this seems like it would be very complicated to implement, but the expressiveness of Spark is such that this was actually pretty simple. Before, you just had a monolithic reduce operation at the master. But now you just add a couple more function calls along the way. So I don't know if people are familiar with Scala. It's a functional language. And so you've got your gradients. You do the reduction, the summation, you parallelize that among the slaves. And that's this function right here. And at the slaves, you do the regularization. And it was that straightforward. So that was kind of a nice thing with using Spark for that. And what this brought us in terms of the workflow diagram was this kind of workflow where things are being distributed among slaves, and the overall communication overhead of the data that comes back to the master is reduced as well because of this combination of systems and algorithmic techniques. But we're still left with a problem that things were kind of converging relatively slowly because we were doing kind of vanilla gradient descent to begin with. And the way we addressed this issue was with using iterative parameter mixing, which essentially does a stochastic gradient descent on a per-slave basis. The observation is as follows. So you're allocating data. You're allocating tasks to nodes. And each node is going to see some fixed number of examples, right? Say you've got a cluster, 2 slaves. Each slave has 3 data items. It's going to have to take its share and process those 3 data items in sequence. The problem here is that it's treating those 3 data items independently. Okay, can we do something a little more intelligent with that? And to that end, to be able to process the examples in sequence and use what we learned from the previous example to incorporate into the intermediate results, we had to introduce kind of a GLOM operator, if you will. That is, we're going to map over subsets of the data instead of individual data items. So this is kind of a different programming primitive from just straight up map and reduce, right? You had to acknowledge the fact that I want to address data in chunks as opposed to one data item at a time. And so the old code looks something like this. You've got a single data item. You compute the gradient based on the previous weight vector that you had before. The new code, what happens is you've got data items, individual data items. You glom them together into subsets, into chunks. And then through each chunk here, you iterate it. And as you can see, from here, you're computing a gradient based on the previous value of the weight vector, but you're feeding that back into the weight vector itself as you're computing it. That's kind of the essence of a stochastic gradient descent. And this actually really improved the convergence rates for our algorithm. And again, Spark's expressiveness made this change pretty straightforward to implement. So finally, this was the final workflow diagram for our implementation. I'll just mention some results, not on the SCAD's loaded data, but for some previous experiments that we ran before, where we had data on EC2 reading it from a Hadoop file system. So we have, say, experiment parameters. I think it was on the order of 400,000 URLs, and that would contain, say, 50 million features. But with regularization, you can reduce that to 100,000 useful features for classification. And if we have set the training ratio at 4 benign examples to 1 spammy example, then we can get an accuracy of around 91%, with less than 1% false positives. So, but with this ongoing work, I'm encouraged that, being able to read data from a scheme format, that we can scale our analysis better. There's a potential to process more data to improve the accuracy. And we have some other things ongoing with Spark in terms of system-side, communication-side optimizations that we hope can help things as well. But the overall takeaway here, and I thank you all for bearing with me for this. I explained the experiences developing a distributed learning implementation. Mesos made writing Spark easy because of the decoupling of resource allocation from other kinds of functions that you expect from a distributed computation framework. SCADs, being able to store structured data, made it amenable to analytic and interactive workloads. Spark's programming model made it easy to write algorithmic fixes. And its modularity made it easy to plug in system-centric fixes in terms of broadcast and shuffle, which I didn't get a chance to explain today, but I'm happy to answer questions about that offline.